Hello everybody! Today we will be talking about buffer overflow attacks. First, let's talk about buffers and buffer overflows. Buffer is a region of memory used to temporarily hold data while it's being moved from one place to another. A buffer is used when moving data between processes within a computer. The majority of buffers are implemented in software. Buffers are generally used when there is a difference between the rate at which data is received and the rate at which it can be processed. If we remove buffers, then either we will have data loss or we will have lower bandwidth. Buffer is the act of storing data temporarily in the buffer. It helps in matching the speed of the data stream between the sender and the receiver. If the speed of the sender's transmission is slower than the receiver, then a buffer is created in the main memory of the receiver, and it accumulates the bytes receiving from the sender and vice versa. Uses of I/O buffering. Buffering is done to deal effectively with a speed mismatch between the producer and consumer of the data stream. A buffer is produced in the main memory to heap up the bytes received from the modem. After receiving the data in the buffer, the data get transferred to disk from buffer in a single operation. This process of data transfer is not instantaneous, therefore the modem needs another buffer to store additional incoming data. When the first buffer got filled, then it is requested to translate the data to disk. The modem then starts filling the additional incoming data in the second buffer while the data in the first buffer getting transferred to disk. When both the buffers completed their tasks, then the modem switches back to the first buffer while the data from the second buffer get transferred to the disk. The use of two buffers disintegrates the producer and the consumer of the data, thus minimizes the time requirements between them. Buffering also provides variations for devices that have different data transfer sizes. We have several I/O buffering techniques. The first one is single buffer. A buffer is provided by the operating system to the system portion of the main memory. Block-oriented device. System buffer takes the input. After taking the input, the block gets transferred to the user space by the process, and then the process requests for another block. Two blocks work simultaneously. When one block of data is processed by the user process, the next block is being written. Operating system can swap the processes. Operating system can record the data of system buffer to user processes. Stream-oriented device. A line-at-a-time operation is used for scroll-made terminals. The user inputs one line at a time with a carriage return signaling at the end of a line. The byte-at-a-time operation is used on forms mode terminals when each keystroke is significant. Second one is double buffering. Block-oriented device. There are two buffers in the system. One buffer is used by the driver or controller to store the data while waiting for it to be taken by higher level of the hierarchy. Other buffer is used to store data from the lower level model. Double buffering is also known as buffer swapping. A major disadvantage of double buffering is that the complexity of the process gets increased. If the process performs rapid bursts of I/O, then using double buffering may be deficient. Stream-oriented device. A line-at-a-time I/O, the user process needs to be suspended for input and output unless the process runs ahead of the double buffer. The byte-at-a-time operation, double buffers, offers no advantage over a single buffer of twice the length. Third one is circular buffer. When more than two buffers are used, the collection of buffers is itself referred to as a circular buffer. In circular buffer, the data do not directly pass from the producer to the consumer because the data would change due to overwriting of buffers before they had been consumed. The producer can only fill up the buffer I-1 while data in buffer I is waiting to be consumed. Let's move to buffer overflow. Buffer overrun, also known as buffer overrun, occurs when the volume of data exceeds the storage capacity of the memory buffer. As a result, the program attempting to write the data to the buffer overwrites adjacent memory locations. Buffer overflows can affect all types of software. They typically result from malformed inputs or failure to allocate enough space for the buffer. If the transaction overwrites executable code, it can cause the program to behave unpredictably and generate incorrect results, memory access errors, or crashes. Here is an example of buffer overflow. A buffer for login credentials may be designed to expect username and password inputs of 8 bytes. So if a transaction involves an input of 10 bytes, which is 2 bytes more than expected, the program may write the excess data past the buffer boundary. Okay, now let's talk about our main topic, buffer overflow attacks. Attackers exploit buffer overflow issues by overwriting the memory of an application. This changes the execution path of the program, triggering a response that damages files or exposes private information. For example, an attacker may introduce an extra code, sending new instructions to the application to gain access to IT systems. If attackers know the memory layout program, they can intentionally feed input that the buffer cannot store and overwrite areas that hold executable code, replacing it with their own code. For example, an attacker can overwrite a pointer. A pointer is an object that points to another area in memory and point it to an exploited payload to gain control over the program. Now let's examine different types of buffer overflow attacks. First, we have stack-based buffer overflows. Stack-based buffer overflows are more common and leverage stack memory that only exists during execution time of a function. A technically inclined user may exploit stack-based buffer overflows to manipulate the program to their advantage in one of the several ways. The first one is by overwriting a local variable that is located near the vulnerable buffer on the stack in order to change the behavior of the program. The second one is by overwriting the return address in a stack frame to point the code selected by the attacker, usually called the shellcode. Once the function returns, execution will resume at the attacker's shellcode. Third one is by overwriting a function pointer or exception handler to point to the shellcode, which is subsequently executed. And the fourth one is by overwriting a local variable or a pointer of a different stack frame, which will be used by the function which owns the frame later. The attacker designs data to cause one of these exploits, then places this data in a buffer supplied to users by the vulnerable code. If the address of the user supplied data used to affect the stack buffer overflow is unpredictable, exploiting a stack buffer overflow to cause remote code execution becomes much more difficult. One technique that can be used to exploit such a buffer overflow is called trampolining. In that technique, an attacker will find a pointer to the vulnerable stack buffer and compute the location of their shellcode relative to that pointer. Then they will use the override to jump to an instruction already in a memory, which will make a second jump. This time, relative to the pointer, the second jump will branch execution into the shellcode. Suitable instructions are often present in large code. Second, we have heap-based attacks. Heap-based attacks are harder to carry out and involve flooding the memory space allocated for a program beyond memory used for current runtime operations. Exploiting is performed by corruption of this data in specific ways to cause application to override internal structures such as linked list pointers. The canonical heap overflow technique overrides dynamic memory allocation linkage such as malloc metadata and uses the resulting pointer exchange to override a program function pointer. The example code indicates that the buffer can be overflow. The vulnerability exists because the buffer could be overflowed. If the user input, which is given by argumentative 1, bigger than 8 bytes. Why 8 bytes? For 32-bit, also known as 4-byte system, we must fill up a double word 32 bits memory. Character size is 1 byte. So if we request a buffer with 5 bytes, the system will allocate 2 double words, which will be 8 bytes. That is why when you input more than 8 bytes, my buffer will be overflowed. Similar standard functions that are technically less vulnerable, such as strncpy and strncat and memcpy, do exist. But the problem with this function is that it is the programmer's responsibility to assert the size of the buffer, not the compiler. In the diagram, we can observe how the buffer overflow can be done. In case A, the main program runs. In case B, program or a function A is called. The next stack frame and the return address are pushed to the stack. Return address keeps the address of the next instruction. Buffer overflow happens when function A receives user input in the form of a string. It creates a fixed size buffer B in case C. The buffer B is larger than it's supposed to be, and overflow happens. It will go beyond the stack frame and may overwrite the return address. Now the pointer will point to the beginning of the buffer. After function A finishes its task, the program counter will initialize to its new return address, which currently points to the beginning of the buffer B. If B has malicious software written on it, after function A returns the buffer, B will begin executing its software and it may damage the device. Various techniques have been used to detect or prevent buffer overflows with various trade-offs. The most reliable way to avoid or prevent buffer overflow is to use automatic protection at the language level. This sort of protection, however, cannot be applied to legacy code, and often technical, business, or cultural constraints call for a vulnerable language. Assembly and C and C++ are popular programming languages that are vulnerable to a buffer overflow, in part because they allow direct memory access and are strongly typed. C provides no built-in protection against accessing or overwriting data in any part of memory. More specifically, it does not check the data written to a buffer is within the boundaries of that buffer. The standard C++ libraries provide many ways to safely buffering data, and C++'s standard template library, STL, provides containers that can optionally perform bound checking if the programmer explicitly calls for checks while accessing data. For example, a vector's member function, add function, performs a bound check and throws an out-of-range exception if bounds check fails. However, C++ behaves just like C if the bounds check is not explicitly called. Techniques to avoid buffer overflow also exist for C. Languages that are strongly typed and do not allow direct memory access, such as COBOL, Java, Python, and others, prevent buffer overflow from occurring in most cases. Many programming languages other than C and C++ provide runtime checking and in some cases even compile time checking, which might send a warning or raise an exception when C or C++ would overwrite data and continue to execute further instructions until erroneous results are obtained, which might or might not cause the program to crash. Examples of such languages include Ada, Eiffel, Lisp, Moda 2, Smalltalk, or Camel, and such C derivatives as Cyclone, Rust, and D. The Java and .NET framework bytecode environments also require bounds checking on all arrays. Nearly every interpreted language will protect against buffer overflows, signaling a well-defined error coding, often where a language provides enough type information to do bounds checking. An option is provided to enable or disable it. Some of the common protections are such, but not limited to, address space randomization, ASLR. It randomly moves around the address space locations of data regions. Typically, buffer overflow attacks need to know the locality of executable code, and randomizing address space makes this virtually impossible. Data execution prevention. It flags certain areas of memory as non-executable or executable, which stops an attack from running code in a non-executable region. Structured Exception Handler Overrides Protection, SCHOP. It helps stop malicious code from attacking. Structured Exception Handling, SEH, a built-in system for managing hardware and software exceptions. It thus prevents an attacker from being able to make use of the SEH override exploitation technique. At the functional level, an SEH override is achieved using a stack-based buffer overflow to overwrite an exception registration record stored on a thread stack. Here are the documents and slides I have used. Special thanks to Yücel Saygın. The slides are based on his lectures. Thank you all for listening to me. Have a nice day.